Hello guys, I'm Nurul Wahida. Welcome to Signals and Networks again. Let's continue our chapter 1. This is module 3, Untitled Convolution. In this course, we only cover the time domain convolution. In this module, we will learn about convolution. Firstly, what is convolution? Convolution means folding. Convolution involves two signals. In time domain convolution, one of the signals needs to be fold and shift. After that, we integrate both signals. Repeat this operation until we get the zero value at the end of positive and negative side of time. To perform the convolution, need to integrate from negative infinity to positive infinity. To perform integration, we change the infinity to a variable tau. These are the steps for convolution. First, fold ht about y-axis and shift to t. Second, multiply. And the third is integrate. Repeat these steps for value of t. If we transform the same signals into frequency domain, no convolution operation needed. Simply doing multiplication between both signals and we get the answer in frequency domain. Generally, convolution were used in the field of numerical analysis and in the design of finite impulse response filters in signal processing. In convolution, there are three mathematical properties you need to know. First is commutative, second property is associative, and the third one is distributive. In commutative properties, if you convolve signal AT with signal BT, the results are the same if you convolve signal BT with signal AT. While in associative properties, if you have three different signals and you want to convolve all of them, the process can be starting by convolve signal AT with signal BT, then convolve the result with signal CT. Or you can convolve signal BT with signal CT first, after that convolve the result with signal AT. The last property is distributive, stated that if you have several signals and an addition process involved, you can convolve the input signal AT with signal BT and signal CT separately, then add the results together. It is the same if you add signal BT with signal CT first, then perform the convolution between the results of addition with the input signal AT. In this slide shows the examples of the visual process of convolution between two signals. The first figure shows convolution between exponential signal ft in blue color with rectangle signal gt in red color. The signal gt is folded and shifted. Then we integrate both signals and get the convolution answer in black colored signal. The second example shows the convolution between two rectangle signals. The amount of yellow is the area of the product computed by the convolution integral. From the results of first example, the response is a smeared version of ft. It begins at t equals to negative 0.5 because we define t as the distance from the tau equals to 0 axis to the center of the white pulse. Okay, let's take a look at the example. This is example 1. Okay, we have two signals and want to perform convolution between these two signals. The first one is Wt and the amplitude equals to 1. And the second signal is Zt. magnitude is 2 and t is 2. Okay, we want to find yt is the convolution of wt with zt. So don't forget, we always use this asterisk symbol as the symbol of convolution. Okay, still remember on the previous slide, to perform integration we need to change the infinity or the t to a variable tau. Okay, so we change instead of using t, we're using tau, so we have w tau 1 and 3 and we have z tau Okay, then remember our steps for convolution. We need to fold the signal. So for this example, let's say I choose z to be manipulated. Okay, so I will fold z signal and then shift the signal. Okay, first step, fold and shift. So we get the z signals. From here we fold the signal, so z negative tau. This is the folded version of the z tau. It's like this, 2 and negative 2. Okay, and then we shift the z signal to t. So we have z t minus tau, and then the z signals becomes since here is negative 2, the tau is negative 2, so t minus tau equals to t minus 2. So the value here is t minus 2, and here equals to 0, so it means that t minus 0 equals to t. Okay, this is z t minus tau. We will proceed the convolution process by convolve the wt signal with the zt minus tau. We multiply both signals and then integrate both signals. We will repeat this operation for values of t. Okay, we start with condition the first condition. We have the fixed signal is w tau 1 and 3, and we have the zt minus tau here. So before that, still remember the equation. We integrate from negative infinity towards infinity. In this case, we use w tau with z t minus tau, delta tau equals to y t. Okay. So let we put the zt minus tau before before 1. So we have the signal here. This one is t. This one is t minus 2. Okay, from here clearly we can see there is no overlap between these two signals. This one is the z t minus tau. This one is omega tau. There is no overlap, so the convolution for both signals equals to 0 since there's no overlapping happen for t less than 1. Okay, non-overlapping. Okay, and then for next condition, we slide or we shift the t signal along the w signal, sorry, the z signal along the w signal. So for the next condition, we have t in between 1 and 2. 2 and 3. So here is t and here is t minus 2. So the overlapping happen here. So yt equals to wt equals to the amplitude of wt equals to 1 and zt equals to 2. So w tau equals to 1 multiply with zt minus tau is 2 delta tau. Oh, I forget the integration. We integrate from we only integrate at the area, at the overlapping area. Okay, so the overlapping area is from 1 to t, so the integration from 1 to t. Okay, solving this integration, we get 2 tau for t and 1, so yt equals to 2t minus 2 for t in between 2 and 1. T is less than 2 and greater than 1. Okay, for the third condition, we shift again the z signal towards positive infinity. So the drawing is like this. This is wt. So we move the z signal towards the positive infinity. So we have t in between 2 and 3. Okay, the overlapping happen here. The overlapping area is here. So we find yt, the convolution between wt and w and z equals to integration from 1 to t wt equals to 1 and zt minus tau equals to 2 d tau. So actually it's same with the condition B. So the answer equals to 2t minus 2 for t in between 3 and 2. Okay, next we shift again the signal zt along the signal w. Okay, so in previous slide we have t in between 2 and 3. So now t is in between 3 and 4. So here is 4. So t is here, and here is t, and here is t minus 2. So the overlap area is here. So yt equals to integration from t minus 2 to 3, okay, from t minus 2, t minus 2 to 3, and the amplitude of w equals to 1 and z equals to 2 delta tau. Okay, solving this equation, we get 2 tau for t3 and t minus 2. And finally, we get yt equals to 6 minus 2t minus 4 equals to 10 minus 2t. Okay, for t in between 4 and 3. Okay, and the next condition, we slide the t in between 4 and 5. So t is here. This one t, this one t minus 2. So the overlapping is here. Yt equals to integration of from t minus 2 to 3, 1 multiply with 2 d tau. So actually the integration is same with the previous condition for t in between 3 and 4. So the answer equals to 10 minus 2t. Okay, next we continue moving the z signal until we get 0 value. So we have here 1 and 3 is the w signal, and then we put the t in between 5 and 6. This one 5 and this one is 6. Okay, t is here. Since t is 2 unit, okay, so 1 unit, it's 4. Okay, at this moment there is no overlapping between w and z signal. So we know that when there is no overlapping, yt equals to 0 for t. Okay, here is t minus 2, this one is t. For t minus 2 greater than 3. Solving this equation, we have t greater than 3 plus 2, meaning that t greater than 5. Okay. Okay, let's write down all the equation of yt. Yt equals to 0 for t less than 1. Yt equals to 2t minus 2 for t in between 1 and 3, and yt equals to 10 minus 2t for t greater than 3 and less than 5, and yt equals to 0 for t greater than 5. Okay, so let's draw the signal of yt. We draw the signal of yt. We have the signal, this yt only have the value in between 1 and 5. Less than 1 is equals to 0, and greater than 5 equals to 0. So I have 1 here, and we have 5 here. So greater than 5 equals to 0, less than 1 equals to 0. And then we have 2t minus 2 from 1 to 3, and we have 10 minus 2t from 3 to 5. Okay, we can write down the signal actually is like this. Okay, that's all for this example, and we will continue and then next video with more examples. Okay, that's all for today. Many thanks for watching. See you in the next video. Bye bye.